This is the fourth video in the series Physics from First Principles. We have now gone over the order of operations, operations done on fractions, and operations involving exponents. In this video, we'll discuss some basic trig that is absolutely essential for introductory physics. But before we get started, I would like to ask that if you find this video helpful, please hit the like button, subscribe if you haven't already, and share this with someone who might also find this helpful. I also encourage you to leave a comment with any suggestions you may have. Let us start with a brief recap of the last video. In the previous lecture video, we went over adding, subtracting, and multiplying exponents. We learned a few things. For one, we learned that we can add exponents whenever we're multiplying numbers with the same base. We can subtract exponents when we divide numbers with the same base. You can change the sign of an exponent by moving it up to the numerator or down to the denominator. Any positive base raised to the 0 is equal to 1. Any negative base raised to the 0 is equal to negative 1. And lastly, we briefly touched on multiplying exponents when distributing them. The answers to the practice problems will be provided at the end of the video. Let's now begin our discussion on one of the most important shapes in all of math and physics, the right triangle. The right triangle is simply a triangle that has one 90-degree angle. It has a longer side, known as the hypotenuse, and two shorter sides, commonly referred to as the legs. The right triangle is extremely useful because it allows us to measure distances and helps us understand how motion and geometry connect. This is done by relating angles to side lengths. This is a pretty exciting moment because it's the first tool we're getting. So what exactly can we do with this new tool? As I just mentioned, the right triangle can help us determine distances, and it can also help us with measurements. Now, of course, with any complex tool, we need to go over the instructions manual. So how do we use it? In order to use the right triangle, you have to be familiar with the Pythagorean theorem. The Pythagorean theorem is a proven relationship between the sides of a right triangle. From it, we get the famous formula a squared plus b squared is equal to c squared that we can use to calculate unknown distances. A and b represent the legs of the right triangle, while c represents the hypotenuse. Using this formula, if we know two sides, we can always find the third. Now, it's important to remember that the Pythagorean theorem only applies to right triangles. If you take an actual trig class, you'll learn about other methods to find the sides and angles of all kinds of triangles using things such as the law of sine and the law of cosine. But I'm like 98% sure that you don't need that for this class. I don't think I can recall a moment when I used it in my Newtonian mechanics course. Maybe perhaps when dealing with vectors, but we'll see. There are, however, a few more trig concepts that we'll need for later chapters, but again, we'll cross that bridge when we get there. Anyhow, let's go ahead and do some example problems that require the use of the Pythagorean theorem. Let us begin with a simple right triangle and no context. Side B has a length of 4, and side C, the hypotenuse, has a length of 5. We want to determine the length of side A. I know I haven't explained much, but pause the video and see how far you can get. The first thing we should do is write down the Pythagorean theorem. A squared plus b squared is equal to c squared. Next, we insert the information that is given. We're looking for side A, so we leave that as a squared, but we replace b squared with 4 squared and c squared with 5 squared. Let's go ahead and evaluate. 4 squared is equal to 16, and 5 squared is equal to 25. So our equation becomes a squared plus 16 is equal to 25. We're looking for a squared, so we must isolate it, and we can do so by subtracting both sides by 16. Now this becomes a squared is equal to 9. We're almost done. The problem is that we want the length of side A, not a squared. So what we must do is take the square root of both sides. This gets rid of the exponent, and so we get that a is equal to 3. Consider this right triangle. Side A has a length of 7, and side B has a length of 4. We want to determine the length of side C, the hypotenuse. Pause the video and give it a try. Again, the first thing we do is write down the Pythagorean theorem. A squared plus b squared is equal to c squared. Now we insert the given information. We replace a squared with 7 squared and b squared with 4 squared. We're looking for c, so c squared stays as is. Next we evaluate. 7 squared is equal to 49 and 4 squared is equal to 16. So this becomes 49 plus 16 is equal to c squared. Adding 49 plus 16 gives us 65, making this c squared is equal to 65. We must now take the square root of both sides. Doing so, we find that c is about 8.1, and this is our answer. Before moving on, I want to make it known that it doesn't really matter which leg we label A or B. The labels themselves don't matter either. When solving distance, for example, you will more frequently see d squared, again for distance, is equal to x squared plus y squared. Or to be even more precise, you'll see something like d is equal to the square root of x squared plus y squared. But again, we'll cross that bridge when we get there. Now, what is important, however, is that you follow the structure of adding the square of the legs and setting that equal to the square of the hypotenuse. Let us now do a more applied type of problem. Consider the following. A ladder leans against the wall. The base is 6 meters from the wall and the ladder is 10 meters long. How high up the wall does the ladder reach? Pause the video and give it a try. First thing we do here is check if we have the correct tool for the job. Remember that the Pythagorean theorem only works for right triangles. I had been explicit about the last two problems being right triangles, but you'll find that in almost all problems you won't be given that. Do we have that shape in our problem? Yes, we do. The wall, ladder, and the floor make the shape of a right triangle. Knowing this, we proceed to write down the theorem. A squared plus b squared is equal to c squared. Now we should identify what's what to plug into our formula. The hypotenuse is the longest side of the right triangle, and it seems that side is the length of the ladder. I should also quickly mention that the hypotenuse is always opposite to the 90-degree angle, so we can put a c equals next to it. Now, as for the legs, well, we know one is 6 meters, and we're trying to find the other leg, which represents the reach of the ladder. Let's go ahead and label the distance from the base of the ladder to the wall as a. Therefore, the side we're looking for, which is again the reach of the ladder on the wall, will be labeled b. Now we can plug in the values into our formula. We replace a squared with 6 squared. We're looking for b, so we leave b squared as is, and we replace c squared with 10 squared. Let's evaluate the exponents. 6 squared is equal to 36, and 10 squared is equal to 100. We want to solve for b squared, so we isolate it by subtracting 36 to both sides. This then becomes b squared is equal to 100 minus 36, which then becomes b squared is equal to 64. Take the square root of both sides and we get b is equal to 8 meters. Now, I haven't gone over the importance of including units with your answers, but let me tell you, do not forget your units. Your professors or teachers will be butt cheeks about this, hitting you with 8 what? Apples, oranges? So don't forget. But yeah, that's pretty much it. We have found how high the ladder reaches up the wall. Consider this next problem. A drone moves 3 meters east and 4 meters north. Find the distance between its starting point and its end point. You know the drill. Pause the video and give it a try. Just as in the last example problem, we need to check if we can solve this problem using the only tool we have. Do we have a right triangle? Yes, we do. Here's a 90-degree angle. Awesome. So we can use the Pythagorean theorem. Let's write it down. A squared plus b squared is equal to c squared. Now we should label what's what. The red arrow is clearly the hypotenuse. It's the longest side and it's opposite to the 90-degree angle. Also notice that it's what represents the distance from the starting point to the end point. We'll put a C here. The yellow arrow is 3 meters. We'll label that A, and this other pinkish leg with length 4 will be B. Now let's input our values into the theorem. A squared gets replaced with 3 squared, and B squared gets replaced with 4 squared. We're looking for C, so C squared stays as is. Now let us evaluate the exponents. 3 squared is equal to 9, and 4 squared is equal to 16. Adding these two, we get that c squared is equal to 25. Take the square root of both sides, and we find that the distance between the starting and ending position of the drone is equal to 5 meters. We've now gone over how to use the right triangle with the Pythagorean theorem. It is now time for me to tell you that our tool has another mode, so to speak. So far, we've used the Pythagorean theorem to find missing distances. Let us call it PT mode for Pythagorean theorem. This has required us to know 2 sides to find a third. But what if instead of 2 sides, we were given 1 side length and an angle? Could we find the length of any other side? The answer is yes. The second mode available in our right triangle tool I call SET, short for SOH-CAH-TOA. Now, before explaining any further, I want to clarify that we don't take into account the 90-degree angle for SET. I mean, we use that to establish that we're dealing with the right triangle, but we need another angle to apply SET. Having now mentioned this, let's go over this new mode. SET is a mnemonic for SOH-CAH-TOA. Remember that now we're considering how to use our tool when all we have is one side and another angle, besides the 90-degree angle. This means that we need to find a way to relate angles to side lengths in a right triangle, and SET helps us do just that. SOH-CAH-TOA is not a formula itself. It's a way to help you recall the following three ratios. SO is to remember that sine theta is equal to opposite over hypotenuse. CA is to remember that cosine theta is equal to adjacent over hypotenuse. And TOA is to remember that tangent theta is equal to opposite over adjacent. Just like with Pythagoras' theorem, SOH-CAH-TOA only works with right triangles. These ratios don't depend on the size of the triangle, only the angle theta, and that's what makes them really useful. Now let's go over the labeling / setup. Hypotenuse is always the hypotenuse. It's the longest side of the right triangle, so that's always easy to label. Or, I should say, for the most part, it's easy to label. Now, as for the adjacent and what's opposite, that's always in reference to the angle that we're using. In this example, the green line is adjacent. When you consider adjacent, I want you to think about next to. Adjacent, next to. Adjacent, next to. Since we've labeled the hypotenuse already, then the other side next to the angle must be the adjacent. Now, as the name suggests, opposite refers to the side that is opposite or across our angle. In this case, it's the pinkish line. So how does SOH-CAH-TOA work? After labeling your triangle, you must consider what information we have and what we're looking for. Just like with PT mode, we should have two knowns and one unknown. That way we can manipulate the equation and solve for the unknown. Let me show you with an example. Consider the following triangle. We are looking for the side with a question mark. First thing we do is determine if we're dealing with the right triangle. We are. This is the 90-degree angle. Awesome. Now we look at the information provided. Do we have two side lengths or one side length and an angle? We have a side length of 10 and an angle of 30 degrees. This tells us what mode to select for our tool. We'll be using SET mode. Let's write it down. SOH-CAH-TOA. Now let's label our triangle. This long side is the hypotenuse, so we can put an H equals here. That means this other side next to our angle is the adjacent side, so we can place an A. The only remaining side is this part of our triangle, the side that we're looking for. You can see it's directly across the angle, so we label it O for opposite. To determine what ratio we use, we consider what's given and what we're looking for. We're looking for the opposite. That means we can already cross out CA because this ratio contains no opposite. So now it's between SO and TOA. Notice that the other piece of information that is given, aside from the angle, is the hypotenuse H. That means that we can cross out the TOA because that ratio doesn't include hypotenuse, leaving us with SO. Once I've determined what ratio I'm using, I like to write it this way. Sine 30 degrees is equal to opposite over hypotenuse. Then I plug in the missing value. Sine 30 degrees is equal to O over 10. I solve for O by isolating, which means multiplying both sides by 10. Now I get O, which is the side we're looking for, is equal to 10 times sine 30 degrees. Before evaluating, I must emphasize, please ensure your calculator is set in degrees mode. If it's set in radian mode, you will get the wrong answer. So after making sure that my calculator is set in degrees mode, I enter the values and I can see that the missing side has a length of 5, and that is our answer. Consider the following. We're again looking for the side with a question mark. Pause the video and give it a try. Is this a right triangle? Yes, it is. What information is given? One side length and an angle. So we'll be working in SET mode. Let's write it down. SOH-CAH-TOA. Let's now label the triangle. This long side is the hypotenuse. That means this side next to the angle is the adjacent side. That's what we're looking for. The opposite side is this side that is across from the angle. We're looking for A, so we can cross out SO. This leaves us with CA and TOA. What else is given? The opposite side is given. That means we can cross out CA, therefore leaving us with TOA. Let's write down tan 45 degrees is equal to opposite over adjacent. We proceed to change the O with a 10, and we can now solve for adjacent. This is done by multiplying both sides by A, then dividing both sides by tan 45. And this leaves us with A is equal to 10 divided by tan 45 degrees. After ensuring our calculator is in degrees mode, we input the values and find that the adjacent side also has a length of 10, and this is our answer. Let's now do a more applied type of problem. You stand next to a steel cable that is 30 meters long and is connected to the top of a building. The angle of elevation between the cable and the ground is 60 degrees. How far from the building are you? Pause the video and give it a try. As with most problems we've done in this video, we first check if we have a right triangle. Do we? Yes, we do. Okay, so we have the right tool for the job. Now we check what information is given. We have a side length and an angle. Therefore, we select SET on our tool and write SOH-CAH-TOA. Let's now label our triangle. Hypotenuse is obvious. It's the longest side of the right triangle. That means this is the adjacent, which is the distance that we're looking for, and this side is the opposite because it's the side across our angle. Now that we know that we're looking for A, we can cross out SO, which means we'll either use the cosine or the tangent ratio. What else is given? The hypotenuse is given. TOA doesn't consider the hypotenuse, therefore we'll use cosine. We write down cosine 60 degrees is equal to adjacent over hypotenuse. This becomes cosine 60 degrees is equal to A over 30. We solve for A by multiplying both sides by 30. Now we get A is equal to 30 times cosine 60 degrees. After checking our calculators in degree mode, we can plug in the values and find that you are 15 meters from the building. Don't forget your units. I want to now use the same problem, but to solve it for something else. Imagine that we didn't know the angle of elevation, but we instead knew how far you were from the building. Could we solve for the angle of elevation? The answer is yes, we could solve for the angle using SET. Now, I know this kind of goes contrary to what I've been saying about choosing PT or SET. If you recall, I mentioned that when you're given two sides, you will choose PT mode to solve for a third side. When you're given a side and an angle, you use SOH-CAH-TOA to solve for another side. So in this case that we're given two sides, why am I saying we use SET? Think about it. We use SET because we're solving for an angle. Notice that the Pythagorean theorem only allows us to solve for sides. There's no angle included in the theorem, but there are angles included in the SOH-CAH-TOA ratios. That's why we use that instead. The process is similar, but instead of solving for a side, we solve for theta. Like always, the first thing we do is make sure we have the right tool for the job. Are we dealing with the right triangle? Yes, that was established in the previous problem. So now what do? We check for what's given and what we need to find. We are given two side lengths, which at first would indicate the use of Pythagoras' theorem. However, notice that we're looking for an angle. We can't use PT to solve for an angle, but we can use SET. So we write SOH-CAH-TOA. Next, we label our triangle. Hypotenuse is 30 meters, adjacent is 50 meters, and the opposite is unknown. Just like we've been doing, we use what's known to determine the unknown. We have hypotenuse and adjacent, meaning we'll use cosine. So we write cosine theta is equal to adjacent over hypotenuse. We insert the values, making this cosine theta is equal to 15 over 30. Remember that to solve for an unknown, we need to isolate it. But how do we isolate theta, which is attached to a cosine? We must use the inverse of cosine, also known as arc cosine. If you look at your calculator right above the sine, cosine, and tan buttons, you should see those same names but with an exponent of -1. Since we want to get rid of the cosine, we're going to multiply both sides of our equation by the inverse of cosine. This will turn our equation into theta is equal to the cosine inverse of 15 over 30. After checking that our calculator is in degree mode, we insert cosine inverse 15 over 30 and we find that theta is equal to 60 degrees, exactly what we had in the previous example. Before finishing, let's quickly go over a summary of what to do. The first thing we do is determine whether our problem makes the shape of a right triangle. If it doesn't, then we cry because the problem will be a bit more difficult. But if it does, then the second thing we do is identify the known and unknown. This is to figure out what mode we'll use. Next, we label the triangle. After that, we plug in the values into our tool. And finally, we solve for the unknown. Anyway, that is it for this lecture video. I leave the following problems for you to try. Notice that they're all word problems, so you need to use your imagination and create a drawing of the situation. Again, I ask that if you found the content helpful, please help me reach a wider audience by hitting the like button, subscribing if you haven't already, and sharing this with someone who might also find this helpful. Here are the answers to the last video's practice problems. I'll see you in the next one.